Okay, welcome back. This is 2 for part 1, exponential equations. And we just solved this one on the last video where we wrote 32 with the same base as 128 and found the answer to be 8 2/3. Okay, so that's where we had finished up last video. We're going to move into some applications that are great for business. Compound interest. This is the compound interest formula. As you see, it's an exponential equation. Okay, it's very important to understand what all these letters mean. Okay, the principal is the amount that you invested. R is the interest rate written as a decimal. If it's a 6% interest rate, we would write R as 0.06. M is how many times per year the interest is compounded. If it's compounded quarterly, then M would be 4. If it's compounded semi-annually, then M would be 2. If it's compounded annually, then M would just be 1. T is the time that we let the money in the bank in years. Okay, years. So if they say we're leaving it in for 6 months, then T would be a half. Morgan invests a bonus of $9,000 at 6% interest, and we're compounding it semi-annually for 4 years. To figure out how much she would earn then, we would put $9,000 in place of P in this formula. We would have 1 plus 0.06 over 2 to the, how many years? 4 years times twice a year power. Okay, so then you can do some of that on your, make the entering it in the calculator. Maybe you want to write this. Actually, we could go a little further. Just say in your calculator, type 9,000 times 1.03 to the 8th. Okay, and see what you get when you take 9,000 times 1.03 to the 8th and round it to the nearest dollar or cent. It's about, I use that squiggly for about, it's not exactly, but it's about $11,400.93. Okay, that's how you use that formula, what everything means. And when we're compounding continuously, something happens where that formula changes and there's this E value here. I want to just show you where that E came from, okay? In your calculator, if you let M get bigger and bigger, in other words, see what you get when you have 1 plus 1 over 100 to the 100th. See what you get when it's 1 plus 1 over 10,000 to the 10,000th. Okay, if you do that, as M gets bigger and bigger, you'll notice you get this number that's like 2.71 something, and it just keeps getting closer and closer. Here, I will do it quickly while you're doing it. If I have 1 plus 1 divided by, I'm going to do 1,000,000. Okay, 1, 2, 3, 4, 5, 6 zeros raised to the millionth power. I end up getting 2.71828. And that's not the exact number, okay? I'm just rounding it. 2.71828, and then it was 0.469. I notice on my calculator there's a number E. It's like the number pi. It's an irrational number. If you'll look on your calculator, it should be above the dividing symbol. E is a number that's found in these types of problems, just like pi was discovered. The calculator approximation of E is 2.71828. 182818, okay, etc. So as you can see, when I put 1,000,000 in this formula, I got really close to this number. That number is an irrational number that's famous in math, just as famous as, well, maybe not as famous in the younger years as pi is. We don't have an E day, but we have a pi day. But anyway, E gets replaced then for that 1 over, for that compounding part, okay? If something's compounded continuously, okay, in other words, like we said, M was getting bigger and bigger. This, how many times is it compounded? Okay, that was getting bigger and bigger. We let it be a million times a year. That's pretty close to continuously compounding. Somebody's sitting there constantly compounding your money, okay? Then we switch to this formula. So if $600 is invested in an account earning 2.75% compounded continuously, how much will be in the account after 5 years? I just have to take my $600 times E to the 0.0275 times 5 power. Okay, I take E to the 0.0275 times 5 power times 600, and that'll tell me how much I will get. Okay, so on my calculator, I go 600 times, I find my E button, which again, mine is, I have to hit second division, and that shows me the number E. E, and then I go to the, which is the up arrow, 0.0275 times 5 power, I get, sorry, 3,083 and 64 cents. That's how much I'll have after 5 years. Very nice, right? That would be sweet that my $600 grow to 3,000. Woo! That would be fantastic. Okay. Biologists studying salmon have found that the oxygen consumption of a yearling salmon increases exponentially with the speed of swimming according to this function, where x is the speed in feet per second. Find the following. Okay, so it's 100 e to the 0.6x. A lot of times, it's not just money where we find these wonderful problems. Oxygen when the fish are still. Well, when the fish are still, how fast are they swimming? 0, right? 0 feet per second. So when the fish are still, then f of x is going to be 100 times e to the 0.6 times 0 power. That's basically e to the 0, which is 1. 100 times 1 is what we're looking for. And so we get 100 units for that oxygen, 100 units. At 2 feet per second, what happens? Well, I stick 2 right into this formula. Okay, so it's 100 e to the 0.6 times 2. 0.6 times 2 is 1.2. Put that in your calculator and make sure you're getting these numbers, okay? About 332 units. So that's another example of where E is used in the real life. Okay, logarithms are, we just need to memorize this, guys. Logs are the inverse of exponential functions. So here is, if I have a to the y equals x, that's the exact same thing as saying y equals log base a of x. Okay, so let's get used to going back and forth from log form to exponential form. If I have log base 3 of 9 equals 2, okay, look at that over here. A is the 3, right? So it's going to be 3 to the y, a to the y power equals x. So 3 squared equals 9. Yeah, that's true. 3 squared does equal 9. Okay, these are saying the exact same thing. They're two different ways. We're used to exponential form. Log form is a way to get the exponent to be the answer to the question. The answer is an exponent, okay? Let's go the other way. If it's written in exponential form, I know that this is true. 1/5 to the negative second power is 25. To write that in this form, remember the answer is the exponent, so it's going to be equals -2. Okay, we have log base a fifth of 25 equals -2. Again, those are the exact same thing that I'm saying. It's one way saying it in log form, one way saying it in exponential form. These are the same thing. It's sort of like 1/2 is the same as 0.5. One of them's in fraction form, one of them's in decimal form, but they're the same number. Okay, log base 10 of 100,000 equals 5. Think about what that means in exponential form. This is our exponent, 5. 10 to the 5th equals 100,000. Okay, that's like saying that. If I have 4 to the negative 3 equals 1 over 64, how would I say that in log? Well, it's going to be equals negative 3 for sure, because the answer is a exponent. It's log base 4 of 1/64 equals negative 3. And this one will have 2 to the negative 4th equals 1/16. Okay, those are just different ways of saying the exact same thing. Oh, I think I have another one here yet. E to the 0 equals 1. That's the same as saying log base E of 1 equals 0. Now, I want you to notice something. We don't usually say log base E. Okay, that's used so much that instead of log base E, we're going to use something called the natural log. That's what natural log means. It means log base E. You'll see an ln on your calculator. Okay? Anyway, we'll get to that in a little bit. Evaluating each of these, sometimes I just put a little equals x beside it. So I can see it. This means 4 to what power equals 64? That's what that's asking. If they say what's a log base 4 of 64, they're saying 4 to what power equals 64? And that answer, of course, would be 3. 4 to the 3rd power. This is saying 2 to what power equals negative 8? Well, that's non-existent. No solution. Undefined. Something like that. Okay, I can't take 2 to a power and get a negative. Okay, 2 to a negative, like 2 to negative 1 is a half. 2 to negative 3 is 1/8, but I never get to 0. Remember, we have a horizontal asymptote there. Log base 5, this is saying 5 to what power is 80? Unfortunately, I don't have a nice number like this 3. 4 to the 3rd was 64. I know that 5 squared is 25, so it must be bigger than 2. I know that 5 cubed is 125. So 80 is somewhere between there. So it's something between 2 and 3. Well, I'd like to know exactly. Is it 2.5? What is it? So we're going to find out how to find that answer, okay? But this is basically your log function like we've been talking about. We always have our base being bigger than 0 and not equal to 1, just like with our exponents. The base, when we talk about an exponential function, our base was always bigger than 0 and not equal to 1. So it's that same thing. This is our base of our exponent, is our base of our log. Okay? If you look at a log function and an exponential function, this is f of x equals 2 to the x. We had graphed that before. We're comfortable with that. This is g of x equals log base 2 of x. It's the inverse. Okay, the x's and y's are switched. This is the line y equals x. I don't know if you remember, but inverse functions are always reflected across the line y equals x. This is what the graph looks like of a natural log. Instead of having a horizontal asymptote of 0, it has a vertical asymptote of 0. Instead of going through 0, 1, it goes through 1, 0. Okay? So anyway, just a quick picture of that for completeness. Properties of logs, you're going to have to know these guys for calculus for sure. It makes taking the derivative so much easier when a log's involved if you have these memorized. Okay, so we will work with these. The log of a product, that's the same as taking the log of the first term plus the log of the second term. Okay, it's just like with exponents. When I have x squared times x cubed, I add the exponents, right? X squared times x cubed is x to the 5th. I add the exponents. That's what they're saying here. The difference, with the quotient, we subtract the exponents. But if I have a power to a power, I multiply. So I'm going to bring that down. R times log base a of x. Log base 2 of 2, or 3 of 3, or 5 of 5. It's always just 1. That's saying a to what power gives me a back? 1. And the log base a of 1 is always 0, no matter what a is. and log base A of A to the R equals R. Tune in for the last part of this section, okay?